you see the screen now?
Yes, ma'am.
Yeah, yeah. So first we discuss the syllabus, okay, what we are having. So when you come to your specialization in the third sem, what you have is you have all inorganic papers, right? So in these inorganic papers, the first paper with the code of CHIC 301 theory, you will be studying about bonding, group theory and its applications. Okay. So you have already studied in your second sem about the symmetry. First sem you studied about the symmetry of elements. Okay. Second sem you studied about the free ion terms. Okay. What are all the terms in a free metal ion? Okay. Now keeping those two in view, you can further go ahead and the next chapter will be your group theory, normal mode analysis and spectral activity. Okay. Then you have the second chapter, molecular orbital theory of metal complexes. Now, keeping all these basic things, that is symmetry, free ion terms, and there is the group theory, the applications what you get from that is you can predict the electronic spectroscopy of the metal complexes and IR and Raman spectroscopy of the complexes. Okay, so these two are the applications. So this from the bonding to group theory, you are getting the two applications chapters you are going to study. Now just look at this chapter. I am going to talk about this electronic spectroscopy chapter. Okay. So in the metal complexes, how can you predict the electronic spectroscopy? Okay. Now coming to the syllabus, this is a very big chapter, very big chapter. So you will be studying about the. I'll give you some introduction today. Today. So after introduction, you have how many types of electronic spectra are there? What are the see any spectra? You will have the selection rules. Fine. Again, in that selection rules, you can have this electric dipole and magnetic dipole transitions. You have orbital selection rules, spin selection rules, relaxation in the selection rules, nature of electronic spectral bands. So you have to study about the bandwidth, band intensity, factors influencing band shapes. So in that you have John Taylor effect. You'll be studying about spectrochemical series. We have already done this, okay? When you were studying about the Crisp theory, we did study about spectrochemical series where we place the strength of the ligands, right? From the weak field to the strong field. Then you have a nephloxitic effect. Then orgeal diagrams, even this we have done second sem, okay, for all D1 and D9 configurations. So this will be a little bit repetition. You have some, so it will be helpful for both your second sem and final sem, third sem. Okay. Then again we are going to study the crystal spectra of octahedral and tetrahedral metal complexes of the 3D metals. Then charge transfer spectra, CT spectra. Then in the strong field, you are going to study about method of descending symmetry. This also we have done the symmetry, how the symmetry is going to change once substitution is taking place. Okay. Then you just studied about object diagrams in your previous sem. This sem we are going to study about two more diagrams, that is correlation diagrams and Tanabe-Sugano diagrams. Correlation means how to correlate, to relate, okay? Weak field, high field, and a strong field. Tanabe Sugano, based on the scientist name, they have given the name. So you are not going to study for all the configurations, only the D2 and D8 configurations. Okay. Then we have to do calculation of 10 DQ values, Raka parameters, and Nephloxitic ratio. Now the books to follow. Anyhow, you are not having the library facility. So, but you just note down these books. So, for electronic spectroscopy, the first book, that is Symmetry and Spectroscopy of Molecules by K. Veera Reddy, second edition. Okay, and one more book is foreign author book is Electron Spectroscopy by the ABP Lever. Okay? These two are the important books. If you just follow the first book also it's enough, or if you can follow my notes and all is also enough. Now I'm changing the screen. Just tell me if you can see this screen. E-Pathashala. E-Pathashala అని ఒక స్క్రీన్ షేర్ చేస్తున్నాను. ఇది కనపడుతుందా? Hello?
Yes. Yes, ma'am.
Yes, ma'am. Yes,
Yes,
ma'am.
madam.
Yeah, fine. So you can see this E-Pathashala, right? Now, గుర్తుందా ఇది? I have told you people from where I got this E-Pathashala.
Good morning, ma'am.
Last time also I have told you, you have to, I'll just show you how to get this E-Pathashala. So మీరు web లో పోయి just click UGC www.ugc.ac.in. Can you see? I'm clicking it. Can you see? UGC, I've clicked. Hello?
Yes, ma'am. Yes, madam.
Yeah.
Yes, ma'am.
Yeah. So when I open this website, ugc.ac.in, okay, what I get is, this is the screen I get. So just scroll down. మొత్తం స్క్రోల్ డౌన్ చేస్తే మీకు కింద ఇక్కడ డిజిటల్ ఇనిషియేటివ్స్ అని ఉంది. Digital initiatives. So in this you have ఈ పీజీ పాఠశాల, మన పీజీ టాపిక్స్ అన్ని దీంట్లో ఉంటాయి. ఈ పీజీ పాఠశాల. I just open this. So this is ఈ పీజీ పాఠశాల. ఈ పీజీ పాఠశాలలో you have all these subjects. So I'm scrolling down. You can see so many subjects. Okay. So chemistry is somewhere here. Can you see chemistry? Chemistry lo entire chapters మొత్తం 565 chapters already. Okay, they are uploaded. Okay, just click on chemistry. Okay. Then I will select the paper. Subject is chemistry. Paper I'm going to select. So you can see all are there: organic, physical, inorganic. Reaction mechanism చెప్పినా మీకు last time ఇంట్రొడక్షన్.
Yes, ma'am.
Yes, ma'am.
Environmental, physical, inorganic లో ఇక్కడ మళ్ళీ చూడండి electronic spectrum. I have taken from this. So click on this inorganic chemistry. Then in this again you have different chapters. So you can have all this crystal field theory. ఇవన్నీ ఉన్నాయి. MOT. I've just started this electronic spectra of coordination complexes. ఇవన్నీ డౌన్లోడ్ చేసుకోవచ్చు. All these material is downloadable. Okay. So you can see here, you can easily download. Okay. So you have the material here. So this is the material. You can just run down and see what are all the materials. Introduction. Today I'll talk about this introduction from this thing. Okay. Then దీంట్లో ఈ టెక్స్ట్ అంటే ఇది whatever you are saying now. You have one more thing, learn more. Learn more అంటే some additional factors for this chapter. Some links are there where you can easily read extra. Okay. Then you have one more called self-learning. Self-learning అంటే సేమ్ ఏదైతే మీకు ఈ టెక్స్ట్ ఉందో అది ఒకరు వీడియో లాగా వచ్చి చెప్తారు. So you have a person teaching you. వినపడిందా? వీడియో వినపడిందా?
Yes, ma'am.
యా. సో మీరు చదవలేకపోతే వినాలనుకుంటే కూడా వినొచ్చు. ఓకే. సో ఈ ఫెసిలిటీస్ అన్ని ఈ పాఠశాలలో ఉన్నాయి. దిస్ ప్యూర్లీ ఫర్ పీజీ. ఓకే. సో మీరు ఎట్లా, సో వాట్ డిడ్ ఐ డూ, ఐ వెంట్ టు యూజీసీ. యూజీసీలో కిందకి వచ్చేసరికి ఈ పాఠశాలలో కెమిస్ట్రీలో ఐ హావ్ సెలెక్టెడ్ మై టాపిక్ ఇన్ఆర్గానిక్ లో మళ్ళీ ఐ హావ్ సెలెక్టెడ్ electronic spectra. So how many chapters are there on electronic spectra? 10 chapters are there. Okay, manaki ivanni avasaram undavu. Whatever is there in your syllabus, only those topics you can take. Okay, only those topics you can take from this. Anyhow, I am giving you the downloaded part of this also. I will send you. Okay, if you cannot download and all, I am providing you material. Okay, but still, if you want to have some other extra information, you can go through this. Okay, so I'll close this window. So we were talking about. So we'll start with the chapter. Now, can you see Pathshala?
Yes, ma'am.
Yeah, fine.
Okay. Yes, ma'am.
We will see this electronic spectroscopy. Spectroscopy ante what is that you understand spectroscopy enduku manaki IR spectra enduku functional groups telustayi kada IR spectra lo. You remember whether hydroxide is there, whether chloride is there, okay, alcohol unda, aldehyde unda,
Yes, ma'am.
you will get to know carbonyl unda,
Yes, ma'am.
whether the bond,
Ketone.
whether the bond is double bond, triple bond, stretching frequencies telustayi. Okay,
Stretching frequency.
so same way electronic spectra also, it will give you some information about the structure of the molecule or the complex. Okay, so if you prepare any compound, you have prepared so many complexes, right, in your previous first sem lo complexes prepare chesam kada. You have got all lovely colors of the complexes. Okay, అన్ని కలర్స్ అని ఎందుకు all of because of this absorption of the visible light. Okay, light absorb చేసుకున్నందుకు you get the complementary color and you see that there is some color to the complex. Organic lab good చేసినారు కదా. Organic lab lo you didn't get any colors. You remember most of them are white color.
Yes, madam.
Yes, ma'am.
Organic every complex there was a color. Anta wonderful colors వచ్చింది మనకి. Organic only dyes you will see the colors, right?
Yes, ma'am.
So inorganic is colorful, very colorful. Okay, so this is
Yes,
all
ma'am.
because of this absorption in the visible range. Okay, so the metal ions, whenever the electron is going from the lower energy to the higher energy,
Higher energy.
yeah, so energy will be absorbed. Because of this absorption, it is showing some color. And where is it absorbing? It is absorbing in the visible region. Okay, and these compounds are colored. Okay, now we'll just see what is the introduction. So that is the reason to know the structure of the complexes or the compounds or the molecules. You should study this electronic spectra, just like other spectra. So this is the introduction part. So I'll not read, but I'll just tell you what is there in this. Okay. If you want to read, you can read. I'm going very slow. Okay. So we know that we have already prepared some complexes and all of them are colored. When you go to organic compounds, they are colorless. We know this very well. We have seen with the experiments also. Okay. But some of the organic molecules are colored. Why are they colored? Because they are having some conjugation of the double bonds. So if you take, for example, beta carotene, okay, which is a terpenoid derived from the isoprene. It is having a orange color. Okay, then some of the complexes are colored because of the electronic configuration or the way the electrons are arranged. Because of this, they will show color. So what are these complexes? I can tell heme group. Blood is red in color, right? Because of the presence of the heme group. Heme group ante emuntadi? You will have an iron atom, so that you have the porphyrin ring. Okay, so it is a complex of iron. Then go to the chlorophyll. Chlorophyll is again green in color because you have a complex that is again a porphyrin ring and a magnesium metal ion. Okay, so because of these complexes, porphyrin ring you have the conjugation of double bonds and they are linked to the magnesium. Blood heme also conjugation of double bonds and you have the metal that is iron. Okay, So these two are, one is showing the red color, one is showing the green color. Okay. Now, in addition to that, when you come to copper sulfate pentahydrate, if no water molecules are there, this will be colorless, copper sulfate. But if I add water to that, it becomes blue in color. So a complex is formed. This is just a salt, copper sulfate. But if I am making it into a complex, then that complex will become blue in color. You have one more coordination complex of iron, that is Prussian blue dye. Okay. So all these are due to the electronic transition. Electronic into electron, transition into moving. Electron is moving from low energy to high energy. During this, it is absorbing the energy from the visible light. Because of this, it is showing the color, and whatever spectroscopy you are studying, because of this, you call it as the electronic, because electron is jumping, right? So we call it as electronic spectroscopy. Okay. So I'll just show you the examples what we have seen. So chlorophyll, this is how you get the electronic spectroscopy. So chlorophyll is absorbing somewhere around 400. See here. So this is for the beta carotene, somewhere around after 400. Okay, and this is hemoglobin between these two. Okay. So each complex or each moiety will absorb at a different wavelengths. So what is that we are going to put on the electronic spectroscopy? You are going to put the molar absorptivity, or some we put the absorption versus the wavelength. Okay, that is what we are going to put on the graph of the spectroscopy. Now we are telling that in the coordination complexes we are seeing the colors. Okay. We know very well that coordination complexes, we have studied that crystal field theory is explaining the some criteria, that is there will be a splitting of the d orbitals. Okay. So we have seen that in octahedral, tetrahedral, we have studied in first sem, right, in bonding chapter, that d orbitals are going to split. So when they are splitting, for example, if I take in octahedral, the d orbitals are going to split into, the 5d orbitals are going to split into two energy levels. The lower energy level is the T2G level, and the higher energy level is the EG level.
EG level.
Yeah. So there is a gap between these two levels, fine. So that energy gap, that much energy you should supply for the electron to jump from the T2G level to the EG level. When I give that much of energy, which is available in the visible region, then the electron is going to jump from the lower energy level to the higher energy level. Once it is jumping from lower energy level to the higher energy level, okay, so I call the lower energy as the ground state and the higher energy as the excited state. Okay, so these two, electron lower energy lo unte ground state lo unnattu, higher energy పోయిందంటే అది ఎగ్జైట్ అయింది అని అర్థం. So you call that as excited state. So once it is absorbing, okay, so you either measure them in the form of wavelengths, which is represented as lambda, or you can even measure them in the form of wave numbers or frequency. Okay. Now just see it, if it is absorbing some at some color, okay, whatever color it exhibits, ante absorb aina color exhibit cheyadu eppude gurbettukondi. If you are seeing some a flower is red in color, that means it is absorbing some green color in the visible light. So you call these colors as complementary colors. Enter with me, complementary colors. So just see here. So the visible region you can tell from 400 to 800 nanometers. Okay. Suppose if it is absorbing between 400 to 450. Okay, the same thing they have converted into wave numbers. These two are inversely proportional. Okay, wavelength is inversely proportional to the wave number. So if this is less, this will be high. This is high, this part will be less. Okay, so I'll not confuse you. I'll just talk about only the wavelengths. Okay, so if I'm talking about 400 to 450 nanometers of wavelength, the color it is going to absorb is violet color. Okay, it is violet color. And what color is it going to show? It is going to show you the yellow color. So if the compound is yellow color, you should know that it is going to absorb the violet color whose range is around 400 to 450. Okay, I said your copper sulfate pentahydrate is blue in color. So what is the range it is going to absorb? The orange range, that is 580 to 650. Okay, 580 to 650. So if it is absorbing violet color wavelength, it will be yellow color. If it is absorbing blue wavelength color, it will be orange. If it is green, then it will show red. If it is absorbing yellow, it will be violet again. If it is orange, it is blue. If it is absorbing red, it will be green. So these two are the complementary colors. Okay, you should know. So if I prepare a compound, it is showing some red color. Okay, or you prepared your nickel DMG, right? Nickel DMG was orange color. So to take the electronic spectra of that, I should know that orange means it has absorbed the blue range. Blue range means I should use the wavelength 450 to 490 to record the electronic spectra of that particular complex. Okay, so this is how this is useful. So you should know the what color it is exhibiting, then what will be the corresponding wavelength at which I have to do the experiment. Okay. And how much energy? The energy is very, very less for an electron to jump from the ground state to the excited state, that is 1.8 to 3.1 electron volts. Okay. And up below this 400 nanometers, you call it as some 200 to 400 nanometers, it will be your ultraviolet UV spectroscopy. And above 700 or above 800, you call it as infrared spectroscopy. Okay. Because of these electronic transitions, we generally see in coordination complexes that these complexes are colored. Okay, they are showing, exhibiting some color. Okay. Now coming to the organic dyes, can you remember any dye? Azides. Okay, azo dye you have prepared. So that azo dye is again orange color, I believe, right? So these orange colored or these organic dyes, why are they colored? Because they have a lot of pi bonding. Okay. We know that once it is a pi bond, electrons are loosely held. Okay. So they can easily jump to the closely placed occupied pi to unoccupied pi star orbitals. Okay. Anti-bonding orbital. So whenever there is a jump from occupied to the unoccupied, okay, you will, the organic molecules are going to show some color, exhibit the color. So this is purely due to organic molecules are showing color purely due to the pi bonding. Okay. And transition metals are colored just because of the splitting of the d orbitals. And these d orbitals are, the energy difference is very less. How much is the difference? It will be around 1.8 to 3.1 electron volts. Now let's see the same thing we have shown in the form of a diagram here. So this is your electromagnetic spectrum, wherein below 700, above 700 I have the IR spectroscopy, and below 400 nanometers we have the UV visible spectroscopy. And this is purely your VGR, that is visible light. Okay, visible light. So violet starts with VGR, right? Violet will be around 400. Okay, so if it is violet in color, the color exhibited will be the complementary color. Violet, what is the color it will exhibit? We know from this thing that if it is violet, it will show yellow color. It will show yellow color. So this is again in the form of a chart they have shown. Okay, color wheel, you can call it as VGR. Okay, either in the form of a scale or the color wheel. Now we'll just take an example of this complex, that is hexahydride aqua titanium 3 plus. This complex, it is absorbing around 500. You see here, it is around 500 nanometers. So if it is around 500 nanometers, okay, that means it is absorbing around this green part, right? So once it is absorbing in the green part, so this is 490 to 560, so that is it is absorbing at the maximum you should see absorbance. So around 500. If it is around 500, it is absorbing green. If it is green, absorbing green, it should be violet in color. So if it is green, it should be generally reddish violet in color. Okay? So that is what they have seen. The color they have given is a bit wrong here. Color of the complex. Okay. So it should be greens and yellow part of the spectrum is absorbed. So the complementary color is violet mixture. Not exactly purely green, yellow and green mixture. So it is showing some violet color. They should have shown some violet color here. This should be the color of the complex. Okay. So they have painted it green, which is wrong. Right? Now we know that. Now looking at the color of the compound, I can tell which is the range. Okay. So if this is a range, how much energy is absorbed? How much energy is absorbed from this wavelength? If I know, I can tell what will be the gap. If it is a gap, I can tell how the d orbitals are splitting. Okay. What is the electronic configuration? Or what is the state of the titanium, whether it is surrounded by a weak field or a strong field, or what is the hybridization, or what is the oxidation number. All this you can predict just from this graph. Okay. Now this electronic spectroscopy, to move further, it depends on the, you have already studied your colorimetry, right? So in colorimetry also you have studied the same thing, visible light absorption. Okay, this is a bit advanced part of the colorimetry. Okay, so in colorimetry also you have seen that it depends on two laws, that is Beer's law and Lambert's law. So wherever we are talking about visible light, it will be naturally these two laws, that is Beer's law and Lambert's law. Okay. Now we will not go into the details of these laws. I'll just tell you what these laws are. So one is when the light is passing through some, are you all following? Yes?
Yes, ma'am. Yes.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
We're talking about the uh, laws which are governing this electronic spectroscopy. Okay. Now these two laws are Beer's law and Lambert's law. Now to understand these laws, what is that? Whenever a light is passed, that is the incident light, is passing through that particular sample, some of it is absorbed, some of it is transmitted. Whenever a light passes, you have four things happening. Four things. One is absorption, okay, by that sample. Then 1 second, I'll just fix it to a battery. So whenever we are having this, light is passing through the solution, what happens? Four things happen. Some light will be absorbed, some light will come out, transmitted, some light will be scattered, okay, and some light will be reflected back, or whatever it is. Okay. So for these two laws, we will take off two things from this, that is the scattering and reflection will remove. We are making them as maybe negligible. Okay. Then we will consider only absorption and transmission. Okay. So whenever light is going, some part is absorbed, some part is transmitted. So these laws, they tell that when you see the Beer's law, they tell that whenever you are passing a monochromatic light means light with single wavelength. Okay, you call it as mono ante okati, single wavelength. When it is passing, okay, it will be inversely proportional to the concentration. That is, if the concentration is increasing, the transmitted light intensity will be less. Intensity of the transmitted light will be less. That is about the baseline. Okay. So that is, it is depending upon the concentration of the absorbing species. Okay. Then we will not go into all this derivation here. We will just see what is the graph, okay, for the baseline. So when I am telling the transmitted light, what I am telling? This is the concentration that is increasing. Okay, concentration increase అయినప్పుడు ఏమవుతుంది? It is falling off. The transmittance is falling. And the intensity of the transmittance is light is decreasing. అంటే తక్కువ concentration ఉన్నప్పుడు ఎక్కువ light will be transmitted out. Okay, and if the concentration is more, the amount of light coming out will be less. Okay, that is what we are seeing from the graph. So you will get a graph like this. This will be exactly opposite if I take absorbance on the y-axis. What happens if I take absorbance? The more the concentration, the more it is going to absorb the light. Okay. So as the concentration increases, the absorption also increases. As the concentration increases, absorption also increases. So absorbance and transmittance are inversely proportional. So if I want the compound to absorb 100%, the transmittance will be 0. If I want the complex to transmit 100%, the absorbance will be 0. Remember that. So these two are inversely proportional. Now coming to the next law, Lambert's law. So one is, we are talking about the concentration. Lambert's law talks about the path length or the medium. What is the length of the medium? Okay. So he tells that as the length increases, as the length of the medium increases, again the intensity of light that is coming out will be less. Again it is inversely proportional. Okay. So the path length, so the transmittance is falling off and off as the path length is increasing. Similarly, if I take absorbance, that means the amount of if I am increasing the amount of the medium, the path length in which the light is passing, okay, then you see that the absorbance increases as the path length. So same criteria the way we have seen for the concentration. Simply I can tell that the absorbance, okay, or the optical density is directly proportional to the concentration as well as to the path length, that is shown as T here, the path length. Okay, so I said it is directly proportional, so we just put a proportionality constant, that is molar extinction coefficient epsilon. Okay, and then you can clearly tell that the Beer-Lambert's law is A is equal to, that is absorbance or OD, optical density, is nothing but here epsilon Ct. C is the concentration. So absorption increases as the concentration increases, and the path length also increases. Okay, so this is directly proportional to these two. So you can simply have one more scale here, which shows that this percentage transmittance. Okay, so it is going from 0 to 100. Okay, absorbance is going from 2 to 0. This is inversely proportional. So if this is 90% transmittance, 0.05 absorbance, very little. It is 100% transmittance, nothing is absorbed. Okay, if the absorbance is complete 2, then nothing is transmitted. Okay? So this is a relationship chart. It shows that these two are inversely proportional. Now coming to the instrumentation part. When you come to the instrumentation part, do you remember what all you have in your colorimetry? Colorimetry, what is that you have? You have a source. Okay. So same thing will be here, even in the spectrophotometer, but the number of prisms which help in the selection of the wavelengths, okay, and which help in the passage of this selection of this monochromatic light, everything will be a bit advanced stage. Okay, and you can do the computerization. You just read from the colorimeter, right? What is there? But here you can do the computerization. Everything can be done. This is a bit advanced of the your colorimeter. Okay, so we have the light source. Light source. You have simply your usual tungsten filament bulb. Okay, so it is a tungsten filament bulb. Once a bulb is switched on, it will give various wavelengths, but we need only one wavelength. So we use filters, right? So if I want at 560 nanometers, if I want at 600 nanometers, if I want at 450 nanometers, I'm going to select the wavelength. Okay, so then it becomes a mono wavelength. Okay, so that monochromatic light, so many wavelengths are there. I'm selecting it with the help of the wavelength selector. We call it as filters also. Then I'm going to get only a single wavelength light, okay, which is falling on the sample. Now some amount is absorbed, okay, some amount is transmitted. That light is going to be detected. That intensity of light is going to be detected with the detector, and that will be computed. And you are going to get a chart like this. You get a graph like this, okay, showing that the OD or the absorbance for that particular complex is so and so at so and so wavelength I've selected, right? Suppose I've selected 500 wavelength, the OD is somewhere around 2 or 1.5 or 1.8, whatever it is. Okay, so the maximum OD it is going to show. So if I know the absorbance, from that this wavelength, this is the absorbance. From that I can easily tell what type of oxidation number of the metal or what type of geometry. We can predict geometry. All other things we can predict from this. So you will not, if deviations are not there in your syllabus, let's skip this. So this is just your summary. So what is that you are going to learn uh, from this electronic spectroscopy is we are going to study how the uh, one second. So what is that we are going to learn from this? We are going to learn the uh, structure, okay, oxidation state of the metal. Structure we mean like whether it is octahedral, tetrahedral, okay, all this. And magnetism you can predict from that. You can tell whether the ligands are strong filled or weak filled. So you have some couple of things you can predict from this. So this was just your introduction. So today we just seen that what are all the uh, why you should study electronic spectroscopy. Okay, what is the information you are going to get? The basics of electronic spectroscopy. What are the principles is governing this electronic spectroscopy? All this is you have already studied in your BS. I'm just refreshing. I'm just refreshing.